So welcome to this talk on C++ optimization for C++11 and onwards. So it's not just 11, but using features of 11. So why? What am I going to talk about, and why am I talking about this? Well, one of the reasons that people use C++ is because they want performance. They want control of what they're doing. And as I've gone through, I've been looking at performance stuff, and people have said, oh, certain things are much faster than something else, you should always do this. And I'm going, oh, hold on. There's a lot of myth and folklore about this, and so maybe there's a better way of thinking about this one. And people saying, oh, you should always use ++A rather than A++, because it's faster and it's better. And really? Okay. Well, we find out whether it is. People say, oh, you should always be doing a shift rather than a divide and whatever, and that's going to make a difference. So if you do division by 4, for instance, you'll find almost all the compilers go, oh, it's a division by 4, I'll do the shift. So actually it makes no difference. Why don't you just write what you intend rather than doing that one? And how would you know? Well, you have to measure. People will say things like avoiding array write because you can't cache an array and you can't use registers and it's slower. And it says, well, really? Okay, well, maybe it is, maybe it's not. But this all strikes me as rather sort of kind of low-level view of the world. And then people say, oh, we should be doing multiple threads. Really? Do you think that's good? Is that the solution? Maybe that's actually not a solution. Maybe that's just another problem disguising itself as a solution. And what about things like move semantics? When are they appropriate? How do they fit into this bigger picture of performance and optimization? And how do caches fit in here? Cache-friendly programming. Great. Sounds like a good idea. What does that actually mean, and when is it appropriate? So what I've come to the conclusion is that actually that there's a whole process, that performance and optimization is not a thing, it's a process. It's a method. It's a way of thinking. And so this is the story that I sort of kind of find myself repeating in my head again and again when I'm lying awake at night, is what do I do about an application? You start off with the application, it's too slow for some definition of whatever too slow is. You know, how fast is fast enough is the first question I ask. Does it really matter you've shaved 2 nanoseconds off the startup time of your program? Possibly not. So you start profiling or timing and you start looking at that and you go, okay, fine. So we at least got to the point where we're now measuring. Some people don't even get to that point. They start just sort of, oh, it's obviously there, and just making some guesses as to where things are. Probably not a good idea to guess these days. Machines and compilers are quite complex things. So first of all, why don't we go and find the unnecessary calls and operations? You end up calling a lot of stuff that you don't need to call. You're calling a database in a loop, or you're doing something that you don't need to do. And often these are quite surprising. You go, really? That takes the time? I didn't realize that was going to be the thing that's slowing it down. And when you get rid of that, maybe then you're fast enough. So what is fast enough? First question. There's no point in making things just faster all the time, and because if that doesn't actually yield any value for your business, then don't. Stop when it's fast enough. First of all, define what fast enough is. Notice that this here is, in fact, mostly just waste. There isn't stuff, this is just getting rid of things. It's not like, oh, I've profiled this and loading this configuration file is the problem. It's just like, well, okay. Maybe that is. If it was loading another file, why am I loading that? Don't go and optimize the loading of that file. Don't load it. It's waste. These are not really the parts of your application. And so, to use Venkat's stuff from the keynote this morning, you've failed to be simple. You've done more than you need. It's not actually the essential part of your application. Usually you just get rid of the stuff you don't need and get rid of all that lot, and then can we actually get down to the application itself. So that's the first thing. Get rid of all the waste, because that's just not helpful. Doesn't make it faster. Eliminate it. The next thing is, right, okay, now I start running my profiler and I find out that malloc or memcomp or memcopy is at the top. This is quite common. I've seen people doing stuff in telephony, and we worked out there was 130 calls to malloc for every request that came in. It was just like ridiculous amount of memory allocation. Why? Why were they doing all that lot? Well, as you'll see as we go through, malloc is really a bad thing to do in many ways. It's also a lack of simplicity, because first of all, malloc is a way of saying, please go and find me some memory that's not in use, which is another way of saying, please find me some memory that's cold and not in the cache. Oh, right, so deliberately make me go and do something that's slow. Right, okay, so by the time I found all that lot, I've gone and done this one. Now I've got empty memory. So the next thing I now have to do is to go and initialize it. That means copying a load of stuff in. I have to do that again. Right, okay, and the reason I'm doing this malloc is because I've destroyed the previous one. So I'm then going to throw it all away. So I'm doing an allocation and a copy and an initialization and throwing it away rather than keeping the original one. So actually, again, this is just one of these unnecessary calls. You keep doing this. Why are you doing that one? Don't go and make malloc faster just by installing JEmalloc or the Google one or whatever. Get rid of it. It's fast. Don't do this one. Work out why you can do that one here. Memcopy, memcomp. You may be surprised by finding some of these. You may, for instance, find out that this is really due to temporaries. It's not what you're doing. You're doing string 1 plus string 2 plus string 3. Oh, that appears to be doing an awful lot of memory allocation. Why are we doing that one? Why are we using lots of temporaries? Maybe we can avoid that one. Maybe we can use emplacement. Maybe move semantics will come and help us. So this is one of the reasons we need to look in C++11 for that. There are differences between GCC version 4 and GCC version 5 on this one. If you're using Visual Studio, you're already in the GCC 5 world. Right, now we've got rid of a whole pile of waste and stuff we don't have to do, and we got rid of some of that sort of non-simple stuff. We actually end up with the application itself. The real stuff, the real algorithm, and the thing we need to do. At this point, we now start going, now it's worth starting to worry about my algorithms. Now am I going to be dealing with order n, order n squared, order log n, order 1, all that kind of stuff becomes more relevant because we've got rid of the waste. We've got rid of the stuff that's hiding the real thing. Maybe caching is important to us, caching at the application level. But this requires us to know about things like our operational profile, by which I mean knowing what operations you have, the access patterns. Is this read dominated? Are you write dominated? What's actually happening? You need domain knowledge at this point to know how big your data is, how it's accessed. That's really where you're going to get a lot of your optimizations at this level. And right down at the bottom level, if you really need to go faster than that, then you can start worrying about things like memory bandwidth and data layout and cache-aware programming, but it doesn't make a difference if you're doing these ones here. So back to this, a lot of these things here are really just picking parts out of here at the wrong time. And trying to do stuff down here when you're making mistakes up here is not going to help you. So for me, performance is a process by which you just chew your way down, get rid of stuff you don't need, then start working on the real stuff. Then you can get into your algorithmics, and then you can start saying, oh, now I can make the machine go fast. Right, well, that's the talk, really. OK. Oh, you want more? Right. It's a multi-level problem. You start at architecture, and it's your design. How do you actually design out some of these problems? Not how do you optimize them, how do you just make sure they don't actually happen or need? I've talked about domain knowledge, knowing about access patterns, structures, etc. How do you use things like the STL? The STL is really powerful. Used well, it's great. Used badly, it's going to be slow. And I've got some lovely numbers to show you just how slow it can be. A lot of applications do string handling badly. It can consume a lot of your time. So a little bit of that, maybe. Memory allocation, some stuff about move semantics. We also need to look at modern machines, CPUs, compilers, and what do they do, and caches. Get some tools. Start profiling, see what you've got. That's the first thing you need to do, is to learn some of those tools. Right. I'm going to go through this relatively quickly. Andre covered some of that this morning. But modern CPUs have got long pipelines. They do lots of things in parallel. Pipeline stalls are expensive, so you have to make sure that you can keep the CPU busy. It has a lot of branch prediction and other things in there trying to do that one. You may have 4, 6 or more instructions in parallel, if it's available. That was the data dependency stuff Andre was talking about. Out of order execution. So what you write isn't necessarily what happens. It's very difficult to see what happens, and things may start in different orders. Basically, what happens is at runtime, it builds a hardware dependency graph of what those things are and does whatever it can. Branch prediction. Very important to avoid the pipeline stalls. It's a well-studied thing. I think the latest AMD Ryzen processor has got a neural network in it for doing branch prediction. That's how important it is, because a branch prediction, if you get a stall, 15, 20 cycles, well, 20 cycles of stall at 6 instructions in parallel, wow, do the math, and you end up with 120 cycles, 120 instructions you've just not done. That's why it's important. Modern processors may even decide, actually, I can't quite work this one out, but actually, why don't I just work out both of them and then work out what the result was at the end. When the result of the conditional has come in, I'll decide which of the two to keep. Hyperthreading, which is multiple cores on the same thing at the same time, and also things like vectorization. I've not covered things like GPU here. That's a whole other section of stuff, and I'm not covering that. Here's the inside of an Intel, just to give you an idea of some of the complexity. 56 entry instruction decode queue. So you can have, it's got 56 instructions ahead it's looking at. And it's splitting those up into 192 entries. And it's reordering those. So if you think you know what's happening, the answer is you don't. It's don't even worry about it. They've done all that lot for you. And then you've got reservation stations. So if you're used to seeing register 1, there is no register 1. Register 1 is actually it's essentially like a variable in a C or C++ program. It's a name for a piece of silicon currently, a slot on the stack. And so register 1 can mean lots of different places. And there can be multiple things called register 1 at any one time. And it has 8 things it can be doing in parallel here with branches and divides and whatever. So the answer is it's really quite complex inside. Trying to second guess that lot, don't worry about it. I'm not talking at this level, but this is to understand the sort of kind of machines you're programming. Interestingly enough, instructions are free, but memory bandwidth is not. So here's a graph. It could be any process one here. I happen to choose power. And this is the growth in terms of gigaflops per second. This is basic sort of raw CPU power going up like this across generations. And look at the memory bandwidth going up here. It barely goes up. And there was a bit of a jump here because they did some special stuff. But basically, as you can see, you can throw lots of instructions at this. Modern CPUs, you're spending most of your time waiting for memory. One of the consequences of this is that actually only 10 or 20% of the time is actually the CPU doing real work. If you try to get some optimization of that 10 or 20% by turning on O3 and using lots of compiler options, the compiler can only help you in bits of this. Unfortunately, it's your job to try and deal with this part. The compiler can't help you with that. So there's plenty of room for you to optimize and things that the compiler can't do. So it's up to you. Modern machines have cache hierarchies in them. So here's a fairly typical cache hierarchy, multiple cores like this, L1, L2, and L3 caches, and main RAM. 1 to 3 cycles here, 5 to 20 at least, this one here, a shared cache of however many megabytes here, and main memory, 100, 300 cycles, whatever like that. Modern machines are really good at doing this. They're designed to do that. If you try to do concurrency, by the way, you're then trying to do this across here, and that's slow. So this is why you don't want to be doing concurrency and sharing of things. Reading stuff up and down like that, sharing across with that is not going to help you. Here is an interesting set of numbers. So this is Sergei Inochenko's thing, but you'll find this in lots of other places. This is a logarithmic scale. So notice these are orders of magnitude, like this. And we're starting off at simple register operations, less than 1 cycle, because we can have multiple ones there, etc. Memory writes, getting a branch prediction right, 1 or 2 cycles, getting it wrong, 10 to 20 cycles. So there's an order of magnitude there. Noticing things like division is still slow. Nobody's really found a way of making that faster. Calls here are about the same as that, which is interesting. You can get some things also, stuff like all this floating point stuff like this. Do you realize that square root is actually sort of kind of in here? It's actually really rather fast. Notice this one down here, by the way. We've got allocation and deallocation of small objects. Hundreds of cycles. This is your malloc thing. So, and that's basically without taking into account all the cache effects, because you're asking for cold memory. So if you do that one here, so you may actually be up here. But notice you're now however many orders of magnitude out of here. The really slow ones, thread context switch. Context switches are utter killer of performance. So guess what? If you're single-threaded, you don't suffer that most of the time. Good. Throwing an exception. That's not a performance option. Please don't do that in performance code. That's for error handling. Context switch here, just the direct costs, but without all the other ones, the cache misses there. Kernel call, well, you're not going to be making system calls in a tight loop. But everything else here, if you got rid of all those ones, you notice that memory allocation is the dominator. The other thing about this one is we have got orders of magnitude difference in here. And if you try to do this with threads, threads are going to give you an order of magnitude because you've got 8 calls, it's an order of magnitude. You can't make up for this, getting to this fast, just by throwing some threads at it. And guess what? The threads are actually going to make things worse. So first of all, get your single-threaded code working quickly, and then work out how to parallelize it without contention. So that's first thing. Stick over here and try and get memory allocation. That's the other part of the talk. Okay, so we'll carry on with that. Measurement. Basic kind of stuff about orders of magnitude. So you may have order n, which is linear, order 1, which is flat. This is more like hash stuff. This would be linear search. You may have a binary algorithm, order log n, order n squared like this, which would be sort of bubble sort kind of stuff. One of the things to know with that is there's always a multiplicative factor, k. And for small n, you may well find that k dominates. So for small values of n down here, your fancy hash algorithm might actually be slower than a linear search. Your quicksort here, in terms of log n or n log n like this, is not necessarily going to be faster than linear search for small ones. Rob Pike a long time ago said, for small n, this will be better, and n is usually small. So again, small numbers law from Andre this morning. So don't always go for the most complicated algorithm. Work out whether you actually have n big enough to merit some of those larger ones. You're trading stuff off. You can't have everything fast. You have to decide what's going to be fast and what you're prepared to be slow. That's knowing your operational profile, knowing your patterns. If you have a read-dominated system, then you make read fast and you make write slow in comparison. That's the trade-off that you make. For instance, if you're going to say, I'm going to keep all my data in sorted order because I only ever update it once a day, that's great. It makes reads really fast, and once a day you do the sort. But you're not going to go, I'm going to do linear search all the time, I'm going to take it into binary. Simple one here. The games programmers have a terminology for this, array of structs and struct of arrays. You will see this quite a lot. And once you start seeing this pattern, you'll see it a lot. If any of you deal with time series databases, this pops up all the time, by the way, of are you going to have a row store or a column store? If you've ever done anything with analytics databases, it's exactly the same problem, but at the architectural scale. So if I have a struct that has a number of fields in it like this, and I'm just going through here and checking something like this, this means that every time I go through here, I need to check here, and then jump to this one, and then jump to this one, and then jump to this one. And I'm reading the whole of X and using only a little bit of X. In this one here, I'm having all of the integers and all the floats essentially in columns rather than in rows. And now my loop says, oh, I'm going to go through just this column. And this means that I process every byte I read. And there's a term called read amplification, which is if I want to read 1 byte, but I end up reading 64 bytes in order to do this one, then I've got a read amplification of a factor of 64. That's not good. I want to read 64 bytes and use all of them. It's like carrying a suitcase and using only one thing. You know? So you have to be careful about this one. This struct of arrays is often what you'll find that games programmers are using. It also happens to say, look, everything's now dense and linear in memory, and vectorization can help me. Compiler can do that automatically. It could be SSE or AVX, or there are even versions now up to 512. Why is that useful? Well, instead of reading one integer at a time like this, I can now read 4 at a time. So instead of going backwards and forwards every time, I can pick up 4 at a time, or 8 at a time if it's AVX. GCC will do this sort of vectorization of loops if it sees this memory is close together. But you're only going to know whether you can do this if you know your access patterns. Let's look at some generated code. So here is a simple summation loop like this. If I compile this with just the ordinary O2 with no vectorization, I'm going to add, and then I'm going to add and move around 4 bytes at a time. If you look at the 03 vectorized version, I've got this parallel add here, and I'm doing 16. So I'm doing 4 at a time. On my machine, that's 2.5 times faster on that laptop. It's almost for free. It's just because I've laid the memory out in the right direction. I haven't done anything else. I've just put it in a way that works well with the machine. Factor of 2.5. I'll have that. So this array of structure of arrays, you can end up structuring your data if you know about your access patterns. So if I have, back down to this thing here with many fields like this, maybe I'm only using one commonly. It might be something like the key or a timestamp or something like that. Well, why don't I just say, here are the columns that I'm using most of the time. And I'll separate those columns away, the hot columns, away from the cold columns. So that way I can do that one here. So that's my job, is just to know that. The compiler can't know that one. You may be able to measure it at runtime, but that's too late for the compiler. You can separate out the hot columns and do the other ones here. And then what will happen is that the ones that you're accessing like this, your working set, is done for you by the caching hardware. And now you go, well, look, OK, these rows and these ones here are held in the fast memory. Everything else is now cold. So you're using your machine as well as possible. You're now dealing with that 1 to 3 cycles access rather than the 100 to 300 cycles. It's 2 orders of magnitude by doing this, potentially. That's a good start. Again, just reordering your data. Strength reduction, one of Andrei's favorites. Eliminating those operations, we talked about that one, reducing the number of them, changing expensive to less expensive ones. Sometimes we can batch stuff up, loop unrolling. It's a classic example. I put it in more for just a reminder rather than saying this is something you should think about doing. Well, you should think about doing it, but it's, guess what? Everybody knows about that one. So back down to this story, we started off with the get rid of the stupid things and then start looking at the memory allocations and temporaries. This is where things like move semantics come in useful. Move semantics in C++11 are a way of reducing some of the problems that C++03 had. 03 said, I don't know what temporaries are. There was nothing in the language about temporaries. So if you did string 1 plus string 2 and you returned this temporary, it treated that temporary in exactly the same way as if it was an ordinary variable. You couldn't do anything with it. Well, wouldn't it be nice if you say, look, it's a temporary, it's about to go away. Why do I have to allocate memory, copy it out, and then destroy the original? That just seems like wrong. We got malloc. Oh, that's not going to be fast. Oh, copying. Well, that seems like a waste of time. Then I have to throw it away and then carry on doing it. Madness, madness. So with C++11, move semantics came in and said, well, actually, why don't I just take the stuff out of the temporary and move it where I want? Auto pointer was introduced in 98, had move semantics and fought the language all the way. Unique pointer is its replacement and has got that built in. rvalue references, move constructor, move assignment operators, similarly. So what does it look like under the covers? So the 98 version would say, well, I've got a string. So I've got this X here that has a pointer to an array of data like this. So pointing to an array of data here. If I return one by value, it'll end up copying it. So what happens is it says, oh, right, you've got this temporary here. I'll do the allocation. I'll do the copy. I'll assign it, and then delete the original. So allocate, copy, and free, all those kind of threes. That's just wasted. Whereas in the C++11 version, it says, OK, well, since I'm going away, why don't I just go and steal that? So you just pull that pointer across and says, that's mine. And this now has nothing in it. So this does nothing. So we've eliminated this extra waste. And that's available to you in C++11. All of the standard classes do this one. Consider looking at your own classes to do this one if you have temporaries around. Here's the implementation detail. What does it look like? A move constructor like this just does pointer manipulation. It says, right, OK, so I'm pointing at the same thing as he is, and I turn his pointer off with null. The move assignment says I need to delete what I've got first before doing that one. So that's a classic optimization, which leads to the C++11 rule of 0. You may have heard of the rule of 3 that says if you need one of destructor, copy constructor, copy assignment, you probably need all 3. That was what you did in 98. And then when move came along, they turned into the rule of 5. By the way, you probably need all 5, including the move operations. You go like, no, that's just too much, guys. Why don't we just say we're only ever going to use things that copy and move correctly? So that's, from a performance point of view, a good idea. So I had a client that did this one, and they speeded up their stuff by getting rid of their own resource management and including all of it which didn't have move and replacing it by things like unique pointer, and they got a significant improvement in performance and code maintainability, because they just got rid of their code and that had all this pointer management in it and just said unique pointer and get on with it. So use standard value classes like string, vector, map. If you do need to do resource management, use unique pointer and possibly shared pointer inside your own classes. Some examples of memory allocation and how slow it can be. I'm taking 10 million elements and doing pushback or insert into a container like this. So I do 25 allocations on this one with a vector. It's totally allocated 134 megs, but it's currently got 64 megabytes of that. Deck does a large number of these. It's actually 40 megabytes divided by 112 is that many, 78,000. So that's about what this one here is. Deck is actually an array of pages. List, unordered set, and set. You can see they're doing a load of allocation here. So what you're really doing whenever you're doing insert into a set or unordered set or list is testing memory allocator. And we know that memory allocators aren't fast in comparison to other things. So let's not do that too often. We can make this faster, since I have this thing of trying to eliminate that memory allocation. What happens if I say, look, I know how big this thing is going to be, so why don't I say vector with a reserve? Instead of reallocating all that memory all the time, do one reserve like this, one allocation. Hey, it reserves the 40 megabytes required once. So I have a choice between 10 million memory allocations or 1. There's a few orders of magnitude there. Notice also the amount of memory this takes up. This is got 24 or 40 bytes per element. So you can see that's 240 megabytes there as opposed to 40 megabytes there. So I've also saved on memory, which is going to be useful in terms of things like caching. I get dense linear access with vectors. Vector is your friend, and vector reserve is also your friend. That was writing. What about reading? So reading from containers. I got some stuff here about, I've got a container, I'm going to do some random numbers and do some random lookup inside it. Let's see what happens there. Let's try linear search. Let's look at some specialist methods, etc. Piece of code here. Don't need to understand all the details. I'm just doing a whole pile of pushbacks or inserts. I'm just going around here. I've got my clock before and afterwards, and every 1,000 or so, I'm just putting out the number so I can do graphs. I'm not going to show you all the detail of that one. And I'm doing a linear find here. This one, by the way, is just to stop the optimizer getting rid of everything, because otherwise it goes, you're not using the result, and we'll throw all the answers away. Be very careful when using profiling with optimized code. Well, what does this tell us? So I'm doing 100 lookups, small out of 10 million, like this. So vector looks like this, and list looks like this, and set is even slower. Okay, right. Interestingly enough, there's about a factor of 7 or 8 between the ones which store stuff densely together and these ones which don't. These ones use pointers. Notice that this uses more memory and this is slower, and this is really just to do with memory bandwidth. It's just how fast can I read this stuff? And this is why list and these other ones are slower than these ones, because these are denser in memory. It's a memory bandwidth issue. Pointers in data structures are just going to slow you down. If you want to try and get speed, then see if you can work out how to avoid having to go and chase a whole pile of pointers. Obviously, linear search is not the most optimal thing, and you wouldn't choose to use a set or an unordered set in order to do a linear find. That would just be a wrong thing to do. So let's actually start using the container correctly, and it either has logarithmic or hash-based lookup like this, and there we go. It's much faster. So that would then be, this is order n, this is order log n, and this is order 1. So there's some differences. When you've got 10 million, it is going to make a difference. So it's notably faster. But we had got some domain knowledge that we haven't actually used at this point, which we'll come back to. unordered set versus set like this, if you start measuring this, you'll actually notice that you'll still end up, depending what the type is, you may end up saying, actually, look, memcomp ends up being in the top of my list. I'm doing a lot of comparisons. So you often find at this point, right, now it's worth starting to understand what the memory comparison is. Remember, we've got get rid of the stupid operations, get rid of the memory allocations. Now we can start looking at things like memcomp and how we're doing our algorithms. We're down into that order log n, order 1 type of stuff. There was an optimization I tried, and I discovered that, guess what, the GCC library had already done it. If I had got a set with integers like this, it had already decided that it knew how to do integers. It didn't need to hash the integer. It just said, I'll do the integer. So when I tried to write my own hashing function, I ended up with the same speed. If it was a float, notice a float, same size, is slower. Why? Because it goes, oh, I have to hash all those bytes. So I can write my own hashing thing and basically says, well, why don't you just take the float and convert it to an integer and use that, and I'm back to that speed. So if you're using hashes, watch out for the speed of the hash. If you see memcomp at the top, you probably have got something that's saying, I'm doing a hash and I'm doing byte-wise comparison. Whereas if you're using things like int like this, you may be using integer comparison, which can be inlined rather than memcomp call. So watch out for hashing. If you are using hashing, make sure that you're not putting a lot of time into your hash function. I had one where I ended up with changing from a triple of database and table and key names of 3 strings. I ended up with lots of memcomp, and I realized that actually if I concatenate them together, I can get 1 comparison rather than 3 comparisons, and I got myself a factor of 3 just by doing that. Domain knowledge. Given that I know that I've inserted the numbers in linear order, then I can say they're already sorted. So I can actually use order log n, a binary lookup on vector. So it's interesting enough that I've gone now, remember this was, I was looking at 100, it was quite slow, but now these ones, vector and dec, are faster than set. They're not, so that's order log n. This is order log n, but through pointers, and this is an order 1. So that one still wins, but these are not unrespectable. Also, the size of this in memory is much smaller. So watch out for those ones, kind of things. Domain knowledge. Something I definitely want you to think about is this is probably where you're going to get the most stuff out of this one, which is understanding your domain patterns. What are the operational profiles? What performance levels? What's good enough? What's your data? How big is it? What's its distribution? Is you've got lots of things the same? Is it all lots of small things but with some occasional big things? What's the distribution of requests? How often is it updated? So I've got some questions for you to think about when you're thinking about building data structures for performance. And these are the 6 questions. I'm going to go through those now in a bit of detail. That's a summary. Primary key access. I'm going to look up this thing by key, and I'm going to get a value out of it. That's probably the most common thing. It's very useful. You can say, well, it could be order 1 through a hash, or I could have a binary search, or if n is small, I can just even do linear search. If it's 10, who cares about all this stuff? Just get at that. You only need operator equals equals at this point. You don't need anything more. You can also split it up, so you can start doing it on multiple machines or multiple threads. All that stuff works very nicely to avoid contention. Examples, product catalog. If I'm trying to look up a product there, or customer records, web sessions which are sticky. No SQL things say it's key value store. Memcache, for instance, there's no way of iterating through the keys. You can only look up a key, and that's it. You can put one in and look it up. You can't actually go and find out all the keys. So that's the most common form of thing. Actually, the whole World Wide Web is like this one. The key is just called the URL. Do you need secondary non-primary key access? Do you need to look up by something other than the key? So if you need to do that, you need secondary indexes. That you may get a secondary database index like that. Are you trying to find parts of a record? Do you need to do things on metadata like when it happened, etc., rather than the key value itself, author, whatever? Maybe you need to go to full text search. This is significantly more work. You have to decide whether you really need this one. As an example, I said primary key access on the web is URL. Non-primary key access is Google. They're quite different. One has made a business, that's a business, the other one isn't. It's usually slower. This is an interesting one, and this is one that often people forget about, is what do you need in terms of bulk access or range scans? If you go, well, actually, look, I'm trying to find, I'm doing a data logging application, I want to see the value of this, or the engine temperature over a particular range or whatever, I probably want to go from this time to this time. I want to go and get a single point, I want to go and get a range of points. So there's some implied ordering about this one, and that will be because you're ordering on time. So other things with hashes, you don't get that. If you try to use a hash, you won't get this ordering. If you try to hash the key for time, then it's spread out everywhere. So you have to know whether you need this one, because if you're paying for ordering when you don't need it, it's slower. You have to go, this is going to be order log n rather than order 1. Cursors, traversal of state, etc. You may find it slow to get somewhere to do the seek, and then you're pulling up a whole pile of things as you go. Hadoop, for instance, the big data stuff is a range scan based view. You get this nice dense linear access. Watch out for read and write amplification at this point, although bulk access very important. If you don't do this, then you'll end up going slow. As an example, if you have a REST API, it doesn't do this, because you want to go, well, I'll go and get this one, and then I'm going to get the next element, and then I'm going to get the next element, and then the next element like this. You're going backwards and forwards rather than one call, go and get me everything. Work out whether you need this one. Same with this is sometimes called the n+1 problem. Read to write ratio. Very important to understand how much you do with this one here. If you have a high read thing, then you have caches. Caches work really well, but then you have to make some decisions around what do I do about cache write through and write back, and cache eviction, how big is the cache, etc. How do I keep multiple ones coherent? And I'm probably going to have some indexing structures. That's great. But maybe you're operating in a high write environment. You're doing data logging. I want to go and get all of the values for, I'm monitoring a chemical plant or a ship or an airplane or something. I want lots of data coming in, or maybe just log files out of my application out of a bunch of servers. Caches don't help me when I'm doing that, except they probably help me to cache the indexing structure. I had one client that said, we have an 8-core machine and it goes about 1.5 cores speed. They were doing process control and data logging. I said, well, that's not really surprising, because you are locking everything all at once. You've got one big lock in front of everything that says, right, lock all the data structures and everything else, update this one value and unlock it. Surprise, surprise, you've serialized your application. I said, look, your indexing structure is essentially read-only. So your metadata is often read-heavy. You're doing 1,000 or 10,000 points coming in per second, and once every 10 minutes you might change the indexing structure. It's like 5 or 6 orders of magnitude difference there. Why are you making the 0.001% case slow down the 99.999% case? Why don't you use a reader-writer lock, and so that all the readers can carry on in parallel and do all their writing, so you split up the writers for the different parts because they're all writing in different places, but you only have one lock on the metadata. In fact, the best way they could have done that was use atomics at the bottom and one locker on the metadata. But it's important to understand that. Even once you've understood how big that is, the next thing to understand is now, what is your working set size? How much data are you actually dealing with on a regular basis? How much of that is going to fit in main memory? Does it fit on a single machine? Does it fit into your L1 cache? How do you fit those ones? Maybe you need your indexing structures in memory, but not on disk. You say, look, I'm going to have my indexing structure in memory, and then make one call to disk. Maybe you do that. As an example, if I'm doing a news website like this, yeah, everybody's looking at today's news like this. What happened last year? Well, whatever. So a few accesses to this. If you're doing logging and monitoring, maybe you're saying, well, actually, I'm trying to work out what's happening right now, and occasionally I need to find out what happened to this machine last year. It's very much biased to this end. And you may find, look, that fits in the cache, even though I've got a lot of data. The accesses are all one place. If, however, I go to the airport, then you probably find that there's a few people here with some frequent flyers and some crew who have lots of access to the passport. Most people fly once or twice a year. So actually, this is a very long, flat tail, and suddenly this is now a load of disk accesses, because I can't fit all of the passports into memory here. You have to understand, and that is exactly the same thing. Go and look this one up, but know the data distribution. And the last one that people often forget is about consistency of data. How many copies of that data do you have around? how far out of synchronization can they be? If I've got something on my screen here, does it have to be exactly the same as that? Is 10 minutes delay okay? Overnight? I don't know. If, for instance, you're trying to sell the last seat on the airline, well, you need to have one copy of that and everybody comes into that. That's then an ACID sort of transaction you have to deal with, but you've limited your scalability. If you're saying, well, actually, look, the product catalog changes once a day, I can then distribute that nice and easily without that. So understand whether you need that. Your reference data, your metadata, for instance, may well be less consistent than the actual transaction data. So back to the performance story. We start off, it's too slow. We're profiling. We're trying to understand where we're spending our time. First of all, find the unnecessary waste, get rid of it. Don't optimize it, just get rid of it. It's not helping you. At this point, you may well find that you've now gotten your memory allocation. So we've seen now that malloc and copying and those other things can cause problems, and temporaries. So we can use move semantics and other things to get rid of this one. We can pre-allocate our memory, like a vector reserve and those other things to try and do that one. We've worked out how getting that closer in memory works better for us. We've seen how we make choices between order 1, order n, order log n, all those sort of kind of things like that. That's actually the real part of where you have to know about what's going on here. This is your operational profile that says, I know that these things are only this big. I can do it in this area. My data items are only 3 bytes long, or whatever. You can use those things to your advantage. It's mostly this one here. It has this sort of distribution. That's where you get this one. At that point, and only then, is it worth saying, look, if I really need to still go fast, now I can start working out how to make it fit with my cache and hot-cold separation and those kind of things. So here are just some of those ideas, just put down as a sort of kind of an overview. Notice that these really are things which have tens of thousands of cycles and then thousands and hundreds. So it's obviously better to try and sort the ones that are 3 orders of magnitude before these ones here. Don't start here. I often see people going, yeah, we need to kind of work out this kind of stuff. Look, does it matter whether I have a pointer or value there? Don't spend your time here if you're wasting time here. Start here and go left to right. Measure and go down. That's really what this one's about. If anyone has any questions about any of those ones, that's fine. If you want to copy these slides, I'm happy to give those to you. And that is about it, I think, on the whole. It's a multi-level problem. It's not a set of tweaks. It isn't, oh, shall I put the plus before or afterwards? It's a engineering, measurement, fact-based approach to optimization, because you know what you're trying to achieve and you know when it's good enough and you know what properties you can rely on. That's your domain knowledge, and your domain optimizations are going to beat any sort of kind of clever algorithms that you can come up with. Use your tools, understand how they work and what they're telling you, and that's really how you're going to get performance and optimization. It's not just by trying to work out the latest flashy toy that you may see. Okay? Thank you.